We're now looking at exercise 612 offset surveys. Now, an offset survey is a method that surveyors use to measure the area of an irregular block of land. So not the area of a rectangle, not the area of a kite or rhombus or trapezium, something that you know the shape of, but it's an irregular block of land. And they use a process called an offset survey, which is also called a traverse survey. So what the surveyor does, he chooses a diagonal of the field and he calls that the traverse line. Traverse means to cross. And then he measures the offsets, which are perpendicular distances to each corner. Now, that's not going to make sense to you until I show you something now. Let's say that we have a block of land and it's this shape. Let's say I want to find the area of this block of land. Okay, it's an irregular shape. So this is what we use the offset survey for. I'm going to call this corner A, B, C, D, and E. Okay, what the surveyor does, they measure distances. Okay, so they'll pick one diagonal. They might say, right, my main diagonal is going to be from A to D. I'm going to measure that. 1 minute. But then, so I'll just read what this says again. It says, the surveyor chooses a diagonal of the field to be the traverse line. So that's my traverse line. And then he measures the offsets, which are perpendicular distances to each corner. So I'm walking along here. I stop. I look to the left and I can see point B over there is a corner of my field. I keep walking a bit more. I stop here and I look to the right and I can see that E is another corner of the field. I'll move C down here. I move up here again and I look to the left and I can see C is another corner of my field. Okay? What the surveyor will do is put measurements along all of these. So, okay, I'm just going to pretend that each of these is, say, 10. Let's say the distance from there to there is 35. So the surveyor will say, right, I'm going to walk 35 metres, or it could be some other unit. And I'm going to stop here and I'm going to look to the left and I can see that 55 metres to the left, I've got one corner of my field. I'm then going to walk another 10 metres. We start from A, we walk 35 metres, we look to the left, and we can see point B is 55 metres away in that corner. Let's say this distance here is 10 metres. I walk another 10 metres and I look to the right and I can see that point E is, let's say, 40 metres to the right. This is what the surveyor sketches. He might walk another 20 metres. I'm just making these numbers up. I look to the left and I can see another corner of the field, and let's say that that distance is 35 metres. And then walking, let's say walking another 35 metres, again, I end up at the other end of the field. So a traverse survey, drawn out properly, will look like that. Can anyone tell me what the actual distance from A to D is? So 35 plus 10 plus 20 plus another 35, yeah, it's 100. Now this is how you draw it. That is the proper survey, but he doesn't draw that on his page. Surveyor entry. That's not what the surveyor draws. He hasn't got time to do that on the field. This is what he does. He draws this. He goes, I'm starting at A. That's position 0. I walk 35 metres. From point A, you always put 0 because that's the starting point. I walk 35 metres, but when I've walked up to here, I look to the left, and 55 metres to the left is point B. This is what he draws in his notebook. This is his page. He doesn't draw that. He draws that when he gets back to the office. But on the field, he draws this, starting at point A, 0. Walk 35 metres to the left, 55 metres, I see point B. I walk another 10 metres. So, therefore, how far have I walked so far? Up to here. So he puts 45. Get it? And then he looks to the left, no, to the right this time, and 40 metres over to the right, he can see point E in his field. He then moves another 20 metres. So I've just gone up to here so far. So I write 65 here, and then I look to the left. I'm here. I look to the left, 35 metres to the left. I can see point C. Great. And then I'm up to here. I'm 65 so far. That's 45, 65. Another 35 gives me 100 metres. And I put, wait, that shouldn't be there. And then I stop at point D. So what he draws in the field is this. A, 0, 35, 45, 65, 100. This is a cumulative total. It accumulates. We just keep adding. So, in other words, the distance from A to D is 100. Got it? When he's 65 metres up, he looks to the left, point C is over there. When he's 35 metres up from A, he looks to the left, B is 55 metres to the right. When he's travelled 45 metres from here, he looks to the right, he can see point E. So what you'll need to know how to do is the following. You'll need to know how to go from the notebook entry to the diagram, okay, or from the diagram to the notebook entry. And then we're just going to work out the perimeter of the field and the area of the field. Now these are all perpendiculars. They're all right angle triangles. You're actually not going to find doing the area and perimeter of this field difficult at all, okay? Yes. Yes, you always put right angles. Every time you look to the left or to the right, they're always right angles. It's a, yes, it is. So this one is a, no, it's a trapezium. Yeah, so all these are parallel. So, okay, let's work out some distances. So let's calculate the distance. All right, I'll just let you write that down, and then we're going to calculate some distances. Should have used a ruler. That is a straight line from A to D. These are all straight lines out. And AB, BC, CD, they're all straight lines, DE and AE. BCD is not one continuous line, it bends. Okay, it's two separate straight lines. One, I want to calculate distance DE. Now to do that, I'm going to draw the right angle triangle that DE is in. Now be careful. There's D, there's E, there's the right angle. What's this length along here? Girls, what's this? 40, but what's this? It's not, what do you do with these two numbers? Yes, you add them. So to get DE, I've got 35 plus 20 here, which is 55, and 40 down there. Are we okay? So it's actually 55. So I use Pythagoras' theorem. DE squared equals, what do we got? To work out DE. Can you see? How do we work out DE squared? Guys, Pythag.
55 squared
plus 40 squared. So DE squared is 55 squared plus 40 squared. So DE squared is whatever, and DE is going to be the square root of whatever you're getting there. Does anyone have an answer for me, please? So DE squared is 4,625. DE is the square root of that, which is 68. Lovely. Will do. To the nearest metre. 68 metres. Oh, these are all in metres. Okay? So 68 metres to the nearest whole number or to the nearest metre. The next one I want to do is to calculate the distance BC. So what I've got to do, I can only do it if it's in a right angle triangle. So calculate the distance BC. I can draw the shape that it's coming from, and I will, okay? I need to draw, BC is part of this trapezium, so I'm going to draw the trapezium. I don't have a ruler on me, but BC is there. I can see I've got 35 up there, 55 there, and what's this length here? 30. So write them out. I've got 35. This is 20 plus 10, which is 30, and this is 55. But if I want to work out BC, I need a right angle triangle to do that. So what dimensions should I put on this right angle triangle? Yeah, this bit down here is 20 because that's 55 and that's 35. What is this length here? 30. Right angle, I've got right angles here. So therefore, BC squared. So I've taken this whole trapezium. I'm breaking this up into a right angle triangle because we can only work out, we're only using Pythagoras to do this. Pythagoras' theorem. So therefore, BC squared is 20 squared plus 30 squared, which is 400 plus 1300. So BC is the square root of 1300, which is 36.0 to the nearest meter. Okay. I looked at where BC was coming from and it's part of this trapezium. So I got 35, 55, and this length here is 20 and 10. Can you see that? Every time you see a distance, that's 35 up to there. Then it's 10 from there to there, 20 from there to there, and 35 all the way to the top. All right, okay. I need this right angle triangle. If this whole thing's 55 and that's 35, this bit must be 20 because 20 and 35 makes 55. The next thing we want to do is calculate the area, but I don't want you doing 4 separate triangles. The 2 triangles on the right-hand side of the diagram can be done as one triangle. Yeah. To calculate the area of the field, girls, this is what I'm going to do. See this triangle on the right? There are 2 triangles, but you know what? You can do it as one big triangle. And if you want to save time, you will do it. No, you can't do that on the other side, unfortunately. But the right-hand side of this diagram, in other words, the shape ADE, you can do it as one big triangle instead of 2 small ones. And I recommend that you do that. So what's the distance from A to D? Look at your notebook entry. 100. And this is 40. So I'm going to draw that triangle now. I'm doing this one first. And I'm labeling it as DEA. So going back up, I'm drawing this triangle on the right, ADE. It's 100 base, perpendicular height 40. So I've got 140. Are we okay? That's one bit of it. That's the right-hand side of the field. Now, if you're lucky, you won't get shapes with trapeziums in them, and you'll have 2 triangles on the other side as well, and you can do them as one. So is an area equal to half times the base times the height, which is a half of what? A half of 100 times 40. So, very good. 2,000 meters squared. Yep. That's part 1. Then we've got more areas to do. Unfortunately, we have to do all the others separately. We've got a triangle, we've got a trapezium, and we've got another triangle. And because none of them are stuck together, we have to do them all separately. So I'm just going to the diagram. This looks like 35 and 35. That's 55, that's 35, this is 30. This is 35 and 55. So what I've done, one sec, I've gone back up here. Look, I've got this triangle here, 35, 35. I've got this trapezium, 35, 30, 55. And I've got this triangle here, 55, 35. I've drawn them all down there. You're going to have to work out, unfortunately, because the 2 triangles are not joined, you're going to have to work out the area of each one separately, just using your formulas. Area is a half times the base times the height, which is a half of Well, they're both the same. 35 times 35, which is, someone's got to give me an answer. We'll do the bottom triangle as well, and then we'll do the trapezium last. Got it? So what's the half of 35 times 35?
35 times 35.
What's the answer? Exactly. Point. Exactly. Meters squared. Right. This triangle down here is 55, 35. A half of 35 times 55. Answer. I don't know where I'm going to fit my...
35 times 35.
Yeah. And then we do a half of 35 times 55 and we get 0.5 meters squared. What's the area of a trapezium? We did it last lesson. A plus B over 2 times H. Now what's your A and B? Guys, that's 35 as well. So this is a trapezium, guys. Two parallel sides are your A and B. So it's the parallel sides are 35 plus 55 divided by 2 times the height of the trapezium is 30. Well, no, what you do is your 35 and 55, that's 90 times 30 if you want, which is 2,700 divided by 2. I think it's 1,350. Anyone got an answer? Yeah. All the underlined ones, I'm not going to write them all out, but everything I've underlined, you now add together those 4 answers. So add your 2,612.5, 1,350 and 962.5. The total area of the field is the same, 4,925 meters squared. Okay? Anyone check it?